So getting back to the definition of the log normal distribution, we've seen this time and time again, but to repeat for emphasis, the definition that a random variable is log normally distributed is that its logarithm is normal. And we'll see in a few moments that if x of t is geometric Brownian motion, its log, the log of its values, this is the log of the value of x at time t. So this is saying fix time t, and look at the log of all the x values at time t. It's saying that those are normally distributed. They have a mean that reflects the starting point. Notice the alpha minus a half sigma squared shift. We discussed that in an earlier module. And we have, again, the familiar sigma squared t variance term. So since the log of x is arithmetic Brownian motion, we can write it this way, that the change in the log of x is arithmetic. In terms of z, we can say the log of x is equal to, because we can add up arithmetic Brownian motion the way we did it before and predict what the log of x of t is. Namely, that the log of x of t, it will always be, for any t, this constant times t plus sigma times a z. Now remember what z of t is. Z of t has a normal distribution with a mean of 0 and a variance of t. So we can think of, if we take the natural log of all the x values at time t, we get this normal distribution with that mean and that variance. Another way of expressing this same thing, and we saw this earlier, is that x at time t is a multiple. It's the value at 0 with a return. And the return is normally distributed. That's normally distributed with a mean of alpha minus a half sigma squared t and a variance of sigma squared t. And again, this is so these are several ways of understanding geometric Brownian motion. It's important that you go through the sequence of steps. The one that is perhaps the most complicated is the very first one, which is to say, why does geometric Brownian motion imply this? This is the mystery. But you should feel comfortable in doing the algebraic steps I next did, which is, if this is normal, then that means that the differential, that's equivalent to saying that the differential is arithmetic Brownian motion. And so we can write it either way. We can think of it in terms of the log of x of t, writing it as a normal including its variable, or, move ahead one. And here, there's an error in this slide. Let's fix it now. If we're looking at the log of xt, we need to insert the log of x0. Let's do that. So that the log of xt is equal to the log of its starting value plus we have a drift term and a variability term. And that ultimately can be written in terms of the multiplier with the normally distributed return. So this mysterious adjustment of the half sigma squared, that was discussed in an earlier module. We'll see it coming from an application of Ito's lemma, and I tried to give a motivating argument as to where it comes from the earlier modeling. But it's an important adjustment. And in fact, if you go back to the module on other binomial models, you'll find that one of the binomial models was called the log normal model, and it includes in it this mysterious half sigma squared adjustment. And so it, in fact, is a model which in light of this limiting result where I need this negative a half sigma squared adjustment to the drift alpha, it actually builds it into the binomial lattice. Turns out, whether you build it in or not, the original binomial lattice we worked with will also, in the limit, produce this adjustment. That adjustment is the effect of compounding returns, much in the same way that the geometric return on a period is smaller than the arithmetic returns. And the adjustment, the reduction from arithmetic to get geometric return is in fact an adjustment related to the variability of returns. So it's related to that as well.